Okay, so here we have the next question on the menu today, and is presenting the situation where we have a boat anchored at a river bank. Okay, this is gonna be what I interpret that as meaning, because this question is not super visual, but we can make it work. Okay, so here we have a boat. Right here. Let's just call that boat. And it's anchored at the riverbank, okay? Due to strong winds, it would move on a quiet lake with a constant velocity of 10 meters per second in a direction negative 30 degrees with respect to the horizontal. Okay, so essentially what that means is that we have a wind speed. Let's call that VW for wind. This has a magnitude of 10 meters per second. And this angle is 30 degrees. 30 degrees, I guess clockwise, because clockwise is typically mentioned as the negative direction of a horizontal. Okay, so this is our wind speed, and our another speed that we have is the river water speed is 15 meters in 15 meters in the positive x direction. So if we define our xy axis like this, that would mean our v water. Okay, maybe VW does not work great for v wind, but let's just call this VH2O, and that's going to be 15 meters per second. Okay, so these two right here, maybe I'll highlight a circle around them. These are environment speeds. Okay, cool. Now the ship wants to cross the river with a velocity of okay, so that's we need to calculate the velocity that the boat needs to go in order to pass like directly across in the y direction like this. Maybe I'll draw that path in red. And we know that this distance is our destination. D for destination. And we know that that is 300 meters. And we need to get there in 1 minute. Okay, so the boat needs a velocity. So VD, this is our velocity to our destination. This will be 300 meters divided by 60 seconds, because it's 1 minute. And this will be in the y direction. Okay, so that's just J for direction, positive J, because we're going up. I know it doesn't it says from A to B. Okay, so we're good on that. And 300 divided by 60, that's I think that's 5 meters per second, just to be 1000% sure. Yeah, okay, so this is what we need: 5 meters per second in the J direction. This is our target velocity. So we need to decide what the boat's velocity is, so that the velocity of the boat plus the environment speeds are going to be equal to our velocity to get directly to our destination. Okay. So to write this out mathematically, we're going to need to do VD, our effective velocity as a result of all our boat, as well as the water that we're in, as well as the wind, is going to be equal to, well, all those things individually. We're going to have VB for boat plus velocity of the wind, W, and plus the velocity of H2O for the water. And well, we're given some of these terms directly, and we're trying to solve for VB. So just like typical algebra, we can take the VW, the wind speed, as well as the water speed, and bring it to the left side of the equation, isolating VB on the right side. But we got to make them negative. So V wind minus V H2O for water. Beautiful. Now that is the V of the boat that we are trying to solve for. Okay, so we need to put in our vector values for here, and then we'll just calculate for VB, and then we will be extremely happy that we found the solution. Okay, so the first thing that we need to consider is VW. This is 10 meters per second, but it is 30 degrees below, or negative 30 degrees with respect to the horizontal. Okay, so you know that if VW looks like this, and this is our horizontal, that's 30 degrees, and this is VW, and that has a magnitude of 10 meters per second. We know that we could break this down into its x and y components like this. Okay, and those two green vectors added together would be the same as VW. And to find these, hey, this actually looks very similar to a right angle triangle. Maybe with the power of trigonometry and SOHCAHTOA, we could find out the VWX and the VWY of these components. Okay, so we could write this as well, VWX, we know that that is adjacent to the angle, and that is in the positive x direction, so that's going to be positive sine 30 times 10. Not sine, cos 30 for adjacent. Be very careful with those, and that's going to be positive times 10 in the I direction, my bad. And then in the j direction, we're going negative, so we got to have a negative term out here. And if we use cos for one, we're going to probably use sine for the other. And you can double check that. I know for a fact that's got to be right. Times 10 in the j direction. Okay, cool. So we can math this out real fast. So cos 30 times 10. Let's ask the calculator, what is that? That's 8.66 in the I direction minus 5 in the j direction. Good thing to keep in mind is that sine 30 is 0.5, same as divide by 2. Okay, so here we have our VW, and VH2O we are given, and VD, our actual final velocity, is also given, so we can just sub those in. Okay, so VD, we had 5 meters per second J, positive 5 meters per second J. So 5J, that corresponds to VD minus, now if you mess up these minuses, big trouble. So we have to be extremely careful here. So now we have to do minus VW. So we're going to put VW in the brackets, but that minus in front, real important. Don't forget that. 8.66 I minus 5J. And this will be VW for the wind. We also got to do another subtraction. That's going to be the velocity of the water. How fast is the water moving? And that's going to be 15 in the positive I direction. And we're going to keep that in the brackets. Positive 15 I. But don't forget about that negative out front. Okay, so that's VH2O. And the result of that calculation is going to be the velocity that the boat needs to have. Okay, cool. So let's continue doing the mathematic magic with this. Oops. Okay, so to multiply out these negatives, we'll have something like this. So 5J minus 8.66 I plus 5J minus 15 J. Oh, that's not 15J, 15I, my bad. That would have been a catastrophic error. Okay, so velocity of the boat. And let's put all of our I terms together. We have so 8.66 and 15 together make negative 23.66 I plus 10 J is equal to the velocity that the boat will need to have to go to follow that path. Now it's going to need the speed and direction. So this is the Cartesian form. We want to get the magnitude and angle of this for our speed and direction. So our magnitude, essentially what this means is here we have 10J. And this is wildly not to scale, so don't believe that this is actually what it looks like. It's just like kind of similar. So negative 23.66 I. And this is right here, VB. Given that it's a right angle triangle, here we will have to do Pythagoras Theorem to get the magnitude of VB. And to write that in a mathematics sense, we have a situation like this. So these double absolute values is to represent the magnitude of the vector. We're going to put it under the root, and we will Pythagoras this theorem. 23.66, square that, plus 10, square that, all under the root. Okay, let's ask my favorite little calculator. What in the world is that? Okay, let's put them under the root. 23.66, square that, plus 10, square that, all under the root. Our velocity that we'll need to have is 25.69 meters per second, and that's it. Okay, but we also need to find the direction, and pretty much what that means is we need to find this angle right here. And so, you know, another right angle situation, we just got to use tangent, right? We have the opposite and the adjacent. We know that our angle is the inverse tan of op over adjacent. In this case, our opposite is 23.6. We only need to really worry about the magnitude in this case, and how we're going to contextualize and give a sign to this angle. You know, we want to go out visually. So just the magnitude is going to be 23.66 divided by 10. Nice and straightforward. Okay, so let's figure out what that is. 23.66 divisé par 10 en français. And we get our angle is going to be 67 degrees counterclockwise from the vertical. Okay, so our final VB vector is going to look a little something like this. This angle, 67 degrees, and the magnitude is 25.69 meters per second. Okay, this is what our velocity of our boat will need to be. Which kind of makes sense. Like we have wind going this way. Wind, maybe let's draw that as blue. Wind, we have water going this way. So it makes sense that we will need to go like against the wind and the water, and we need to like counteract their velocities in order for our boat to travel directly across the stream. Okay, so yeah, this would address this question. I thought that was a really fun time, so let's mark this question as good and keep it moving. Awesome. So there is no above solution. Velocity of boat that a boat should have is 25 0.69 meters per second at an angle 67 degrees counterclockwise from vertical up. Cool.